In this video, I am going to show DPD Designer in action using an amplifier fast circuit envelope model file extracted from PathWave RFIC Design, GoldenGate. I invoke DPD Designer from the Start page, selecting the DPD Designer template and clicking the OK button, which brings up the DPD Designer GUI. It usually comes up like this, with a user-friendly interactive block diagram where each component is sensitive and opens its setup window once you click on it. Alternatively, you can go to the individual tabs on the left side to access the different sections and associated settings. If I go to Power Amplifier, I can see that the tool consumes fast circuit envelope model files and dynamic gain model files. I select FCE and browse to my amplifier model file. This file was extracted at a frequency of 2.412 GHz and 312.5 MHz bandwidth. Before I begin, I want to get to know my PA. For that, I turn on the Show PA characteristics. I will perform a sweep from -20 to 10 dBm and look at the PA compression. A pre-configured graph opens up automatically. I can see the 1 dB compression point and when saturation starts. Looking at the region where the linear output power trace and the actual PA output power trace meet, I can decide the input power for my DPD. I pick -16 dBm. We can go back to the block diagram and select the kind of modulation that we want to put through the amplifier. I choose modulation source. I will input a 5G ENA downlink signal at 2.412 GHz, so I pick FR1. I define a 20 MHz bandwidth. I am not going to use a compact waveform to speed things up, since I anticipate a very short simulation time. I will not enable crest factor reduction for this exercise. Under Advanced Settings, one can modify the modulation settings. I hit Simulate and Show CCDF, and the pre-configured report page pops up once the simulation is done. Notice that here I can find the signal time duration and the sampling rate information. See that the peak-to-average power ratio is displayed. The power complementary cumulative distribution function curve is also provided, showing critical peak-to-average power information, how much time the signal spends at or above a given power level expressed in dBs relative to the average power. Now I am happy to run DPD. I go back to the block diagram and hit DPD application. I am going to run direct DPD. For this DPD mode, we allow users to specify the maximum crest factor expansion and the advanced settings. For modulation analysis, I will instruct DPD to extract all results, ACPR, EVM, and spectrum results. I hit the Run Simulation button. It takes around 12 seconds on the computer I am running this on. Here are the results, nicely arranged on a printable live report page. The red signal is the original signal, the blue signal is the signal through the PA, and the green one is the signal with DPD applied to it. From here, we can see that distortion has been reduced. We can also look at the adjacent channel leakage ratio measurements, EVM, normalized mean square error, power measurements, amplitude distortion, and phase distortion. I will now run dynamic gain DPD. It runs faster. The red signal is the original signal, the blue signal is the signal through the PA, and the green one is the signal with DPD applied to it. Here again, results show that DPD has reduced in-band and out-of-band distortion. Notice that you can remove or add additional information to the report if you want to. I add PA model type and DPD method information using an annotation object that I can populate manually or automatically with a short set of equations. Now, using the Ctrl-P keystroke command, I can print my report.